Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to use specific heat and latent heats in thermodynamic problems. So in the problem we're going to look at, this is kind of a problem from my youth, and I'm going to give kind of the short version here. If you had me in class, you've heard the longer version, but the short version of this class, or of this problem, is I used to work on a charter boat, and one day my boss and I made what are called cannonballs, which are basically just lead fishing weights, and we made 500 pounds worth. So in order to do that, we had to melt 500 pounds of lead. So what we're going to do is, in this example, we're going to try to estimate the energy, the time it would take, and the cost, assuming 12 cents a kilowatt hour, to melt 227 kilograms of lead. All right. So when you're looking at thermodynamic problems, first thing you have to realize here is that there's two different things that are going to happen to that lead. One, its temperature has to come up to its melting point. And two, to melt it, now we're going to have a phase change. So the first thing I'd recommend doing here is a graph. Right? And if you've seen my graph on Introduction to Latent Heat, this is a very similar graph. And what the graph is going to be, it's going to be a graph of the temperature of that lead against heat added. Okay, so we're going to do temperature against heat added. Now, first thing to realize, we did this on kind of a hot July day. So the temperature was probably around 75 degrees. I think it stands to reason that the lead, sitting outside in the afternoon was probably around the same temperature. So the initial temperature was around 75 degrees Fahrenheit, which in centigrade should be around 24 degrees. So the first point on the graph is going to be maybe here, about 24 degrees centigrade. Now the idea here is the lead goes into a giant pot called a melting pot. The melting pot was an electrically driven pot. It had an electrical heat source, and before the lead would start melting, what has to happen is its temperature has to go up. Now, this lead sitting in the pot, this is a fairly large system, and it's not being heated evenly. It's being heated mainly at the surface in contact with the pot itself. So the lead isn't all going to come up to temperature at the same time. But what we're going to do is we're going to assume that this is a slow process, and we are going to assume kind of a uniform temperature for the entire 500 kilograms, or I'm sorry, 227 kilograms of lead. So we got to imagine the lead sitting in the pot, heat transfer to the lead, temperature starts going up, and we're going to assume it goes up linearly. So on this graph, we're going to have this linear part, and that linear part will extend to the melting temperature of lead, which I've got written behind me here, 327 degrees centigrade. In this region, what we're going to use to calculate the energy is the specific heat. Before we do that, however, we're going to talk about the phase change part. So at this point on our graph, that lead would be 327 degrees, but it's still solid. And again, just approximating this as all at the same temperature. And then as heat still transfers to the lead, it's going to start melting, and we're going to assume a constant temperature process for the phase change to some point where it's all melted. So at this point, that lead is all solid. At this point, it is all liquid and ready to pour in the molds. So there's two different regions in this graph that need to be considered when we try to calculate the total energy use. So let's take them one at a time. So going back to this region, this is a temperature change region. So to calculate the energy, we're going to use the specific heat. So we got Q equals mc delta T, which is good in this linear region. In this example, the mass of that lead was around 227 kilograms. The specific heat of lead is around, I'm going to pause this to double check that value. Okay, I'm back. Sorry about that. I just had to double check my thermodynamic values here. So 227 kilograms of lead times the specific heat of lead, which I looked up at 128 joule per kilogram degrees centigrade, times the delta T. Now the delta T is the temperature change on this graph. That's this distance, which is going to be, I'm just going to do this, 327 minus 24. I believe that's 303. 303 degrees centigrade. All right, so what I'm going to do now is I'm going to ask my group of assistants I've got here helping me make this video to calculate that for me. I'm going to have to give them credit in the video, I'm sure. Okay, you said 8 million what? Let's just do this. 8.8 times 10 to the 6 joules. And let's get confirmation here. I want to make sure. 2, 3. Okay, so about 8.8 times 10 to the 6 joules, or about 8.8 million joules. That's how much energy it's going to take in this region. That's the temperature change region. Right. Now, we also have to melt it. So the heat required to melt it on our graph, that's this horizontal distance. This is governed by the latent heats. So Q equals M times the latent heat of fusion. This is not a vaporization problem. If we vaporized that lead, we would have been long dead. So let's see the mass, 227 kilograms. And the latent heat of fusion for lead, and I'm going to look that up. I got 24,500 joule per kilogram. And again, I'm going to go to my assistants here to calculate a value. 5.5 times 10 to the 6 joules. So we've got 8.8 million joules to bring it up to temperature, 5.5 million joules to melt it. The total is the sum of the two. So that's going to be 8.8 plus 5.5 times 10 to the 6 joules. What is that, 14.4? Whoops, 14.3, yeah. 14.3 times 10 to the 6 joules. Total energy required to melt that lead. So, got that one knocked out. Okay, time. Oh, I see I forgot one of the assumptions I wanted to throw in here. The heater of the pot was around a 1500 watt heater. Right. And 1500 watts is a unit of power. And power is energy over time. I'm going to write this out right here. Delta E over delta T. So in this example, the power of the heater was 1500 watts, or 1500 joule per second. The energy transferred to the lead was 14.3 times 10 to the 6 joules. We're going to divide that by the time, delta T. And all we have to do now to get the time is calculate the delta T here. So the delta T is going to be 14.3 times 10 to the 6 over 1500. And I'm going to wait for one of my assistants here to give me a value. I just need 14.3 times 10 to the 6 over 1500. What's it come to? 9,500. So this is approximately 9,500 seconds. Now remember, there's 3,600 hours per second. Would somebody divide that by 3,600 so I can convert that to a more reasonable time frame? Okay, which is about 2.64 hours. And what stuns me about this example is how reasonably accurate it is with all the approximations. Having, when we did this, that was about how long it took all of this process to occur. Okay. Let's see. Time. Done. All right. Cost. Okay. As in like dollar signs here. How much does it cost to do this? So this was an electric heater. When you're dealing with electrical bills, you're charged by what's called the kilowatt hour. And a kilowatt hour is, just like its name implies, you can actually tell exactly what a kilowatt hour is just by taking it at face value. I'm just going to do this right in the middle here. 1 kilowatt hour is equal to 1,000 watts, because kilo means 1,000, times 3,600 seconds per hour, or seconds, because that's what an hour is. So a kilowatt hour is 3.6 times 10 to the 6 joules. Right? So the cost of the energy associated to do this One way to figure it out is this. The cost is, I'm sorry, I'm going to back up a second. I'm going to take our total energy use, 14.3 times 10 to the 6 joules, and I'm just going to multiply by our cost, which is 12 cents per 3.6 times 10 to the 6 joules equals, and you notice the joules cancels, leaves us with cents. And you notice the 10 to the 6 also cancels. Would somebody give me 14.3 times 12 divided by 3.6? 40, let's say about 48 cents approximately. So this was one way to calculate it. We also could have gotten the calculation done another way. The kilowatt hour we actually could have calculated here. If the heater's 1500 watts, that's 1.5 kilowatts. And had we multiplied that by 2.64, we would have a value with units of kilowatt hours, which we could then apply the 12 cents per kilowatt hour to. So again, this was just meant to be a kind of a realistic example. It's a real example from my past life here of how to apply concepts like specific heat and latent heat, and how to relate that to something real, like the time required to get this done and the dollar signs associated with doing it. Now, there's lots of assumptions here that were kind of built in. This wasn't a perfect calculation. Some things that I should mention here. We did not take into account any energy loss from our system there. And while the pot is hot, air would take some of that energy away. Again, the lead did not heat uniformly. I'm sure the bottom of the lead heated, before the top of it, and so forth. So there's lots of, things that make this data not perfect. But usually calculations in physics aren't about being perfect or trying to get significant figures. It's nice just to have an idea of how to estimate quantities, and these are completely reasonable estimates based on the methods that were used. Right. So I hope this video helped demonstrate these concepts. Have a great day.